First of all, to tell you who I am, in case you don't know, I'm Professor Wendy Hall. I'm a Professor of Computer Science at the University of Southampton. It's my pleasure to chair the Milner Award Committee and to make the award every year. And it's my pleasure to introduce and to chair tonight's lecture. Can you please make sure that you've turned your mobile phones off? I've just remembered mine's in there, but I think it's on mute. And for the first time, we've got a bit of an experiment today. We're webcasting this event, and that will mean that people will be able to watch this event live, and they'll be able to send in questions. And Stefan, who is in the audience there, is going to relay one or two of those questions when we come to the Q&A session. So now it's my pleasure to introduce Professor Bernhard Schölkopf and to give you the background to the award and the lecture. The Royal Society Milner Award is supported by Microsoft Research, is given annually for outstanding achievement in computer science by a European researcher. The winner of the award receives a medal and a personal prize of £5,000. The winner is invited to deliver a public lecture on their research at the Society and should be an active researcher in any area of computer science. Professor Bernhard Schölkopf was awarded the 2014 Milner Award for being a pioneer in machine learning whose work defined the field of kernel machines, which are widely used in all areas of science and industry. Professor Schölkopf's scientific interests are in machine learning, causal inference and perception, with applications in fields ranging from medicine to astronomy. He received an MSc in mathematics and the Untitled Memorial Prize from the University of London in 1992, followed in 1994 by the Diploma in Physics from the University of Tübingen. For his PhD in computer science from the Technical University of Berlin, he won the annual dissertation prize of the German Association for Computer Science. Since 2001, he's been a scientific member of the Max Planck Society. Since 2011, as one of the founding directors of a new institute in the area of intelligent systems. He's received several awards, including the J.K. Agrawal Prize for the International Association for Pattern Recognition, the Max Planck Research Award, and the Academy Prize of the Berlin Brandenburg Academy of Sciences and Humanities. He co-founded a successful series of machine learning summer schools and currently acts as co-editor-in-chief for the Journal of Machine Learning Research and Early Development in Open Access, one of my passions, and today the field's flagship journal. So, ladies and gentlemen, I'm very pleased to present this year's Royal Society Milner Award winner, Professor Bernhard Schölkopf.
So thank you very much. Good evening, everybody in the room, and I don't know if someone is following on the web. So I work at the Max Planck Institute for Intelligent Systems, and our long-term goal is to understand the organizing principles of complex behavior. So on these videos that you see up here, there's different types of complex behavior or simple to complex behavior. You see a white blood cell in pursuit of bacteria. You see a frog trying to catch an insect. You see a human doing something called parkour. And finally, you see a group of humans engaged in some collective behavior, performing a double chorus Bach cantata. So I included this latter one. You don't hear it yet, but I'm going to turn up the volume a little bit later, because there's a very nice, or maybe I'll try it a little bit in the background. There's a very nice story about this. So apparently, Mozart, when he visited Leipzig, he attended a performance of this cantata, and he liked it so much that he was trying to get his hands on the score. Is it too loud? Can you still hear me? So he was trying to get his hands on the score, and apparently that wasn't possible. So he decided to just sit down, in a pub in the evening, and just wrote it down from memory. So that's the story. It's not clear whether this is true, but it's a nice story, and it illustrates some of the things that humans can do. Now, obviously, we are very far from doing these kind of things in artificial systems. But we believe that some of these accomplishments are related to the fact that biological systems can learn. So my field of research is to get computers to learn. And this has many applications in science and industry. So for instance, suppose you are going on an online shopping site and you're looking for a glass circular cutter. I hope that's the right English term. So from past purchases of other customers, we can learn that people buying this kind of item like to buy some other things to go with it. And we can then make recommendations, such as this thing here called, called a balaclava, or this baseball bat. The brand name is Hooligan. And I think this kind of analysis can also lead to surprising insights. So for instance, it seems to be the case that burglars shopping at Amazon also fancy rucksacks with Batman wings. Now, many of us deal with data as scientists, and drawing conclusions from data is something we're good at. So let's assume we've measured two observables, x and y, and we found the points to lie approximately in a straight line. So we might be willing to infer a corresponding law of nature. However, Leibniz already pointed out that if we scatter spots of ink randomly on a piece of paper, for instance by shaking a quill pen, we can also find a mathematical equation satisfied by these points. So he argued that we wouldn't call this a law of nature, because no matter how the points are distributed, there always exists such an equation. According to Leibniz, the equation needs to be simple. This begs the question, what makes an equation simple? And a number of people have thought about this issue, including the mathematicians Hermann Weyl and Gregory Chaitin. Now, the physicist Rutherford took a pragmatic view. He said that if there's a law, it should be evident from the data. So if your experiment needs statistics or inference, you ought to have done a better experiment. So I like this quotation, but I will still try to convince you that there are interesting inference problems that are non-trivial. So problems where better experiments are not enough. We find lots of such problems in biology, for instance in perception. So let's look at some images here, images of handwritten digits. This looks like an easy case of inference, or empirical inference as we call it. You have no problem recognizing these digits. Now let me do a simple transformation of the images, applying just a fixed permutation of the pixels, in other words mixing up the images in a fixed way. So mathematically, if we process such images with a computer, we usually represent them as vectors, so as sequences of numbers, where each number characterizes the brightness of one of these pixels. So we have just changed the sequence of numbers, just the ordering of these numbers, and this doesn't really make a difference to a computer. However, to us as human perceivers, the problem suddenly looks a lot harder. So how can that be? Well, the answer is that the original images only appeared easy to us because we've been trained, our brain has been trained on such images all our lives, extracting statistical regularities. Or in the words of Horace Barlow, a neurophysiologist, the brain is nothing but a statistical decision organ. In fact, non-trivial problems don't only occur in perception, but they are abundant in science, also in scientific inference. So here's an example of such a task, and I won't go into great detail. It's a task from computational biology where we need to classify human DNA sequence locations. And we have a large data set to learn this classification from, and we use something called a support vector machine. And this curve measures the performance of this system in some way. And what's interesting about the curve is over here, if we have 10 million training points, we get a performance at 70%, which is very good for this task. So we can learn this problem quite well. But if we go over here on the left, if we only have 1,000 training points, we're down to almost zero. So it's almost like random guessing. So this is a kind of regularity that we wouldn't be able to see if we only looked at a few hundred or 1,000 training examples. But it's there because if we have 10 million points, we are very good at it. So I think this is very interesting, and maybe also a paradigm changing fact that we can solve these problems nowadays with computers. And these problems are characterized usually by several aspects. One is the high dimensionality, so one has to consider many factors simultaneously to find this structure. These regularities are usually complex in the sense of nonlinear, non-stationary, etc. We usually have little prior knowledge. So we don't have a mechanistic model underlying the data. And as a consequence of these three things, we usually need large or big data, as they're nowadays called, big data sets. And of course, then we also need computers to process them, and we need automatic inference methods. So automatic inference methods, that's my field, and I'll try to give you an idea of some of the basics of this field. And one of the basic problems is called generalization. And I'll try to illustrate it with a toy problem. So suppose you've observed this sequence of numbers, 1, 2, 4, 7. So if you want, you can guess what's the next number. 11. So 11 is a very good answer because there's this very simple rule that explains why the next number should be 11. It's called the lazy Cateros sequence because if you have a piece of something, let's say cake, and you want to cut it into the maximum number of pieces using n cuts, then this is the number of pieces you get because each new cut can intersect all previous cuts. So that's what you gain with a new cut. But if you had told me 12 or 13 or 14, there are also very good explanations for that. There's the Fibonacci sequence, there's the sequence of divisors of 28. There's this explanation that a former postdoc of mine came up with. He said it's obviously the decimal expansions of pi and e interleaved. And there's a website, so you can go on the web to the online encyclopedia of integer sequences. You enter these numbers, you get 600 hits, how they can be embedded into a mathematically meaningful sequence. So if you ask the question which continuation is correct, then really there's no way to tell. So philosophers call this the induction problem. Of course, psychologists constructing IQ tests tend to ignore this and nevertheless want to decide what's the right continuation. Now, statistical learning theory, which is the theory underlying our field, asks a slightly different question. It's asking a methodological question. So how do we use the observed data to come up with a law that's correct? So what kind of procedures should we be following to find a law that will probably do almost as well in the future as it has done in the past? That's closer in spirit to what Karl Popper called the Kant's demarcation problem. So it's a question that what separates physics from metaphysics? So what kind of procedures characterize an empirical science? Now, I know that you are not all computer scientists and mathematicians, but let me nevertheless occasionally show some formulas. And don't be intimidated by that. You don't need to follow these formulas. So the simplest scenario for machine learning is called two-class classification or pattern recognition. So this means we're given observations consisting of inputs, so for instance, images of handwritten digits, and class labels. So the inputs are the x's, the class labels are y's. In the simplest case, let's assume the class labels are just plus minus 1. We assume that there is some unknown regularity that generates these observations, and we model this regularity as what's called a probability distribution, Pxy. So this thing here generates these things that we can observe. We assume that this thing is unknown. That's why it's an inference problem. We only have the data, and we want to infer something about this regularity. And our goal is to minimize what's called the expected error or risk. And that's in a sense, the probability of making an error in the future as we draw more and more observations from this unknown regularity. Now, the problem is, I told you already, we don't know this law, so we cannot compute this quantity, let alone minimize it. So we need what's called an induction principle. So we need to sort of approximately try to minimize it based on what we have, and what we have is the training data. So we replace this quantity by its empirical approximation in terms of the training data, and then try to minimize it, minimize this quantity instead of the true thing that we want to minimize over some class of explanations, some class of functions. Another theoretical question is whether this is consistent. And consistent means, does this give us the right answer as we see more and more and eventually infinitely many observations? So do we converge to the right solution? And that's a profound question. And one answer of this question was given by Wapnick and Chervoninkis. You've seen the pictures over here, who worked on this in Russia in the 60s, 70s as PhD students. And they proved that empirical risk minimization, so the procedure of minimizing this quantity, is consistent independent of what the underlying law is, provided that something called the VC dimension of the function class is finite. Now, I don't explain this in detail, but I just want to give you an idea. So if our function class were a linear classifier, so we try to separate data points with straight lines, Suppose we had linear classifiers in R2, so in the plane. So we draw points on a piece of paper, we try to separate them. We ask how many ways can we separate 3 points. Then it turns out there are 8 different ways. And if it's the case that we can realize all these 8 ways, but we can't do it for 4 points anymore, so if there are separations of 4 points that we can't realize, then we say the VC dimension is 3. More generally, in d-dimensional space, we find that the VC dimension is d plus 1, and it thus increases with dimensionality. But there are some interesting cases when we separate the data with a margin, not just with a straight line, but with a straight line that keeps some distance to these points. Then it turns out we can give a bound on this VC dimension, which is independent of the dimensionality and which is inversely proportional to this margin. So we can control this capacity or complexity of function classes even in high-dimensional spaces, and that turns out to be important for machine learning. So the message from this is that for linear function classes with margin, we can give this bound on the VC dimension, and we know how to make the learning process consistent. We can guarantee that in the limit we will find the right answer. And there's a nice trick how to reduce general machine learning problems, nonlinear problems, to this linear case. It's called the kernel trick. And in this trick, we start with a problem that is nonlinear. So for instance, the problem of separating these blue crosses from the red circles. We embed it into a higher dimensional space. So in this case, for instance, by this prescription that computes all products of order 2 in the input variables. And then it turns out, in this case, not always, but in this case, it turns out that suddenly the problem becomes linearly separable. So we can solve it with a straight line, and that's nice. What's even nicer is that using this mapping that I showed on the last slide, we don't actually have to carry out this mapping, because it turns out we can compute dot products of points mapped this way by some simple function in the original space. So we don't actually have to explicitly compute this mapping. Instead, we just compute the dot product in the original space, raise it to the power of 2. It gets even nicer and more general in that we can generalize this to d-dimensional inputs and to products of order p. So we can define this quantity here, which is an example of a so-called kernel. And one can show that this thing here maps into the space of all products of order p in the original measurements. So the kernel trick now consists of taking any dot product algorithm and replacing the dot products with this quantity, the kernel, and this way we are implicitly carrying out the algorithm in this high-dimensional space or feature space. Mathematically, it's the so-called reproducing kernel Hilbert space. And it turns out it doesn't only work for polynomial kernels, but it works for anything that's a so-called positive definite kernel. And kernelizing a linear algorithm can lead to something rather different and interesting. So for instance, if we kernelize principal component analysis, which is one of the best known algorithms for signal processing, we get a nonlinear data analysis method that unifies a number of other approaches. But I won't go into details on this. Now, support vector machines I already briefly mentioned. They also use this idea that we have a nonlinear problem in the input domain. We map it into a higher dimensional space. We separate it, or we solve it linearly there, in this case using a separation with a large margin. And then we get a nonlinear classifier in the input space. And here I have a little video where I start with an almost linear classifier. So I start with a kernel that in some sense is almost linear, and then I gradually turn up the nonlinearity, and then you see how this explanation gets more and more nonlinear and how the data points will eventually be separated. And in practice, these solutions can be computed by a computer program, and it has to solve some numerical problem called a convex quadratic optimization problem. But we don't need to look at these details now. So in all cases, we get nonlinear surfaces in the input domain, and we can do this in many different areas. And this is an example from computer graphics. So these are complicated surfaces in three-dimensional space that correspond to some hyperplane, which is a generalization of a straight line in this high-dimensional space or feature space. Okay, so in the next slides, I want to show you a few machine learning applications from our lab in Tübingen, just to give you an idea of the variety of things that can be solved. So this, on this slide here, this first application, we train a learning machine to predict a virtual X-ray tomography image from a magnetic resonance image. So this is an MRI image, this is a CT image. This virtual image that we have learned, so we have data points, pairs of such images, of both that we have measured for some patients. Then we train this learning machine to predict, given the MR image, a synthetic CT image. And then this virtual image can be used to perform something that's called attenuation correction, which is a necessary step in PET imaging. So PET is positron emission tomography. It's another medical modality in imaging that needs this attenuation correction. So traditionally this has required that people also take an X-ray image, which is not all that healthy because it comes with some radiation exposure. So in this case we can use this synthetic image to get a correct PET image that looks almost identical to the true one. This next example, we train a robot arm to play a Japanese game called kendama. So we first demonstrate, our PhD student demonstrates how the task is done. The robot then first imitates this movement, and it's not going to work. Then subsequently the robot improves it over 100 trials, and we always feed back how far the ball misses this cup. And gradually the robot optimizes the parameters, and finally after 100 trials it has mastered the task, which is kind of similar to how long it takes a human to learn it. But the difference is once the robot can do it, it almost always gets it right. So here's the last application example. Here we use machine learning to reconstruct the most likely static image underlying a video of this tower film proturbulence. And you can, maybe I'll have to play it again. So this is the input data shot through the exhaust of the air conditioning system of our building. And then we switch off the air conditioning to get a ground truth image, and this is actually our reconstruction from these turbulent images, and you can see that it's almost identical to this ground truth. So in all applications of machine learning, there are some issues that need to be addressed, or some crucial questions that need to be addressed in one way or another. And it's nice that kernels provide a unified framework to do so. So they formalize a notion of similarity, so they tell us how do we compare the observations. They induce a linear representation of the data, and it's actually especially nice in this case that we get this representation in a vector space no matter whether the original data was vectorial to begin with. So the original data could also be strings or something else. If we can define a positive definite kernel, we get this representation. And finally, the kernel also encodes the function class used for learning. So I told you at the beginning it's important to think about capacity or complexity of function classes. So function classes are important. The kernel does all the three things at the same time. So that's a nice story, but there's a little bit more to kernels that has developed over the last few years. And the starting point of this was a tutorial example that we included when we wrote a book about kernel methods. So we thought about what could be the simplest possible example to describe in the first chapter. And we came up with this example where we're building a simple classifier, two-class classifier based on these two categories of data, mapping them into the feature space, then just computing means of these two classes of data, and then we could classify a new point based on whether it's closer to the first mean or to the second mean. Now, when we put in the kernels, we noticed that this in the end led to something that looked very familiar. So the microphone went off. So did you hear anything the last 2 minutes? Or were you just politely? We compute the means, we look what's closer. In the end, we get this thing, which looks very familiar to a statistician. What it's basically doing is computing a density estimate of this class, and it computes a density estimate of this other class, and then it sort of classifies based on what's more plausible. We now understand that this is actually an example of something more general. we can not only embed sets of points into this feature space of reproducing kernel Hilbert space, but we can also embed continuous probability distributions into these feature spaces. And by the choice of the kernel, we determine how much information is retained in this embedding. So if we choose a linear kernel, then we only retain the mean or the first moment. If we choose a polynomial kernel, we can decide how much information we retain in terms of the moments. So we retain everything up to moments of the corresponding order. And if we use a different or a specific type of particularly non-linear kernel, we actually retain all information about the data set or all information about the probability distribution. So this has a number of applications that people have been studying over the last years. One of them is, or several special cases that are interesting are the moment generating function known in statistics, the characteristic function known in statistics. We can construct independence tests, homogeneity tests. We can also do Bayes updates. There are some physical realizations of such kernel embeddings. And finally, that's something that I think is new. I was asked also to include some new material here. We can do arithmetics on probability distributions in what I think a fairly elegant way. And I think this is also going to have a number of interesting applications in various fields. So machine learning methods, such as the ones that I've described, they are used all over the place. They are used in your mobile phone, in your camera, and they're used when you search the web. They're used whenever we have lots of data, but little knowledge of the underlying mechanisms. We have a pretty good understanding of how these methods work, provided nobody intervenes in the underlying systems and nothing changes. Unfortunately, that's often unrealistic, and then things can break. So I'll illustrate this with another shopping example. So in this shopping example, the customer is looking for this item here, which is a laptop rucksack, specialized rucksack with a laptop bag. And then Amazon recommends the person should buy a laptop to go with the rucksack. So this feels wrong somehow. And intuitively, we would say that buying the laptop is a cause for buying the rucksack. And buying the rucksack is an effect. So in some sense, both of these things, the cause and the effect, contain information about the other one. The cause contains information about the effect because it controls the effect. The effect contains information about the cause because it carries a footprint of the cause. But it feels like they're not the same things. But funnily, the mutual information is symmetric. So actually, the amount of information in some sense is the same. And if we only look at that quantity, the statistical quantity, the directionality is lost. So here's another example to illustrate the difference between dependence and causation. There's a strong, this is probably well known, there's a strong correlation between the number of storks living in a country and the birth rate among humans. So this is the data, you don't need to look at it. But even though there's this strong correlation, we would not try to increase the birth rate, the human birth rate, by increasing the number of storks. So the statistical model does not make predictions for this kind of interventions. So in summary, it seems that causal links create dependence, but vice versa, it's more complicated. And the physicist and philosopher Reichenbach had a profound insight into what is the link between causality and statistics from his point of view, which I share. And this insight is still at the core of modern causal inference methods. So he was saying, he formulated this thing he called the common cause principle, which said that if there are two variables, so for instance the storks and the birth rate, which are statistically dependent, then there is another variable, z, that causally influences both. So we could think of it as the level of industrialization in a country, or maybe it's a whole set of different confounders, as we call them. So the situation is x and y are dependent, therefore there's something that influences them both, and as special cases, this something might coincide with x or with y. So these two things are contained as special cases in this first part of the postulate. The second part of the postulate says that this variable z screens x and y from each other in the sense that given z, the observables become independent. So if we were to compare only countries that are at the same stage of industrialization, etc., whatever we need to control for, then we would expect that the birth rate and the storks become independent. So here's a model of causality, a mathematical model that can be shown to satisfy the Reichenbach principle. So we assume, and this gets a little bit technical, but afterwards it will be less technical again, so bear with me. We assume we have a set of observables, these xi, so these are quantities we observe, that are connected by arrows representing direct causal links. This object connecting them is called a graph. Each observable is determined by its parents in the graph. So the things that have arrows pointing to our observable, they are called parents. This is nothing, it's not physical parents, they're just parents in the graph. So each observable is controlled by its parents and by a variable u, which is not drawn here. And this u stands for unexplained. Sometimes it's called noise, but it's actually something that is crucial and that we need to use afterwards. These noises, as we call them in short, they are random. And this randomness of the noises then implies that everything else becomes random as well. And we get what's called a joint probability distribution. This probability distribution has something called conditional independencies that are specified by the so-called Markov condition. This object that we get like this is something called a graphical model. Graphical models are very popular in machine learning. And every graphical model with respect to such a directed acyclic graph can be written this way, but not uniquely. So the functional causal model actually contains more specific information than the graphical model. So the functional causal model allows us to predict the effect of interventions. So we set a variable to a certain value, then these equations are actually assignments as they are. They tell us what will happen to other variables. And the functional causal model even lets us make statements about so-called counterfactuals, which is something that especially philosophers thinking about causality discuss a lot. So the central question of causal inference is the following. Suppose we observe a lot of data. So we watch these observables for a long time. We measure a lot of data, maybe so much that we can estimate this underlying distribution. So we estimate the statistical law that has generated the data. Can we, from this estimate, can we recover the graph? In other words, can we infer the causal links from purely observational data? So that's the profound scientific question. And there's a partial answer that people have worked out. It's very elegant. And this answer essentially says that by conditional independence testing, we can infer, usually not the correct graph, but we can infer a class of graphs, those that are consistent with the predicted conditional independence properties, and we can prove that it contains the correct graph under assumptions. And essentially the idea is that we sort of track how the information about the noise spreads through the graph, and we check which node has information about what. And if we can do these tests, then we can infer these properties of the graph. Now there's several problems about this answer, and I'll briefly mention them and tell you a few ideas of how we can get around this. One problem is that this distribution may contain accidental conditional independencies that mislead us about the graph structure. This is something called unfaithfulness. Another problem is that if these functions on the graph, so remember each node was a function of its parents in the noise, if these functions look very complex, then actually this statistical test for conditional independence based on finite sets of observations becomes arbitrarily hard. So we shouldn't assume we can do that. In fact, by default, we should assume we can't do it. And finally, if we have only two variables, so in this case, we can't do any conditional independence testing because conditional statements always involve three variables. So there's nothing we can do whatsoever. If we have two variables only, the problem is not solvable. At least this approach, using this approach. Now the two-variable problem is the problem of deciding what is cause and what is effect. And of course, we're not the first ones to deal with this. So this is an example here. The philosopher Nietzsche wrote about this, or he wrote about the error of mistaking cause for consequence. And he called it reason's intrinsic form of corruption. So is there anything we can do about this? So the first idea, how to get a handle on this cause-effect problem, is to make an assumption that states that cause and mechanism should be independent. So cause and mechanism should be independent. We can formalize this mathematically, but maybe I've already bored you enough with mathematics, so I'll rather show you a picture. So this picture shows something called a Bechet chair. So when we see this object here, our brain makes the assumption that the object out there in the world and the mechanism by which the light from the object reaches our brain are independent. We can violate this assumption by looking at the object from a very specific point. In this case, the point marked by this little hole. And if we do that, our brain gets fooled and we perceive a 3D structure which in reality isn't there. So this kind of effect is used a lot in art. Another nice example of the same effect can be seen not far from here in the National Gallery. This is a painting from 1533 by Hans Holbein the Younger. It contains this strange object at the bottom. It seems strangely disconnected from the rest of the painting. And upon looking from the side over here, the object turns into a skull. So 2 years later, Holbein became king's painter to Henry VIII, but we don't know if this was related to this impressive display of skill. So mathematically, our assumptions can be visualized as follows. And just very briefly, we have some input distribution, P of x. We have a mechanism, f of x, which we assume for simplicity to be invertible. Then this mechanism turns the input or the cause distribution into a distribution over the effect. And the interesting thing is that if the mechanism is non-trivial, so it's not just a straight line, then the effect in some sense carries a footprint of the mechanism, because where this function was flat, the effect distribution will have higher mass. So if this object and this mechanism are independent, then we can actually mathematically prove, using a certain formalization of what we mean by this independence, that the output distribution or the effect distribution and the mechanism are not independent. So this is one formalization. If we have independence in the forward direction, we have strict dependence in the backward direction. So, and this can be analyzed in various ways, for instance, using methods of information geometry. Here's a second idea how we can handle the two-variable case. So in this second idea, we first look at what this functional causal model actually looks like for just two variables. So we have our two observable variables. I told you that at every variable there's a noise or unexplained variable. In the case of x, let's assume x is the cause of y, then this is the only thing affecting x, so we can actually identify x with this thing. Let's forget about this and simplify. So we are left with these three things. And we know by assumption that x and u are independent. And if we now ask ourselves, if we take such a model where y is a function of x and this unobserved quantity, if we ask ourselves how rich is this class of functions, for instance, if this noise variable were a variable switching between d different values randomly, then using such a mechanism we could implement a switching mechanism between d different functions turning x into y. And of course the noise need not be discrete, it can be a continuous variable. We could switch between a continuous number of different functions mapping x to y, and it seems intuitive that it should be impossible to infer something like this from data. It's just too rich a class of models, and that's what we learn in machine learning, that we need to restrict the class of models. And one way to do this, in this case, is to use an additivity assumption, that the noise, which sort of was too complex in its action on the function, should be additive. And it turns out if we assume this, then we can prove that for most possible distributions of x and y that we might observe, so the observational data is just this distribution, for most of these distributions we can either find a forward explanation with additive noise or a backward one, but not both at the same time. And this can be specified exactly, but I think it's not the right place to do that. So we now have two ideas. They lead to algorithms, methods, and then we try to test them. And we've collected a number of such cause-effect problems for which we have observational data, plus a reasonable idea of what's the correct causal direction or the ground truth. And if we apply our methods on this kind of data, We do find that both these methods perform better than chance in telling cause from effect, even though it's the two-variable problem that people used to think cannot really be decided. And we can apply, you see a video over here, we can apply the same kind of method also to classify the direction of time series. And more recently, together with a number of colleagues, of videos. And there's a nice illustration of this kind of effect. So this is the video for which this classification would be easy, at least for us as humans. And it's also interesting to show this video because this was possibly the first time that humans could actually perceive how it looks when time were flowing backward, because maybe you have noticed that something changed in this video apparently. So this is a video that was shot by the Lumiere brothers in 1896. And apparently when they showed this, a typical way of showing it was that the operator would first go forward and at some point start cranking the handle backwards. And then people could suddenly see something like this, which must have been amazing at the time. So essentially this problem of classifying whether time flows forward or backward is mathematically very similar to the problem of telling cause from effect. Okay. So where do we stand regarding this central problem of causal inference? The problem was that we have this graph, it generates a joint distribution over observables, and we want to know whether we can recover the graph from this distribution or from the observational data. The incomplete answer was we track how the noise information spreads. We can't recover the whole graph, we can recover it up to some equivalences. I tried to give you some partial new answers. One was to postulate this independence of noise and functions. And somehow here the idea is, informally, as the noise spreads through the graph, it picks up information about these functions. It picks up footprints of these functions. And that also gives us information about the flow of information, about the directionality, etc. The second idea was to restrict the function classes here, because in that case, we can't explain all possible observational distribution anymore. And finally, we have also thought about the problem of trying to combine everything, and it seems to us this worked most elegantly in a different framework, in a non-statistical one, where we replace statistical information or Shannon entropy by something called Kolmogorov complexity, which is quite a fascinating concept to describe the complexity of objects. And what's nice about this, without going into detail, is that we can formulate functional models similar to what I showed you before, only that in this case, on each node, we have a program running on some Turing machine that takes as inputs the outputs of other programs, processes them, and one can develop a similar kind of formalism using this Kolmogorov complexity. We get a kind of a theory of graphical models, and we get something, we can prove that this model implies a Markov condition, a causal Markov condition like before, where Shannon entropy is replaced with Kolmogorov complexity. So I told you the basic ideas in a very short time, basic ideas of machine learning and of causal inference, at least I tried. But what I find most interesting is how these two things could potentially benefit from each other. And to conclude the talk, let me show you two brief examples of this. So in the first example, to motivate it, I first want to tell you that it turns out that in some machine learning problems, we are learning to predict effect from cause. So these are problems that we call causal, whereas in other problems, we try to predict cause from effect, and we call those problems anticausal. So for instance, in this visual recognition problem, the cause is someone decides to write a digit 3 and then produces the image of a 3. So the image is the effect, and the class label is the cause, so that's an anticausal problem. And in general, if we want to learn a mapping from x to y, so that's the machine learning problem, we need to estimate properties of the conditional distribution of p of y given x. Now in semi-supervised learning, which is a popular field in machine learning, we try to improve the estimate of p of y given x by additional data from p of x. Of course, that can only possibly help if there's a dependence between p of x and p of y given x. And in the case of causal learning, That's precisely what's ruled out by our assumption of independence of causal mechanism. Hence, in this case, we would predict that semi-supervised learning should not work. But it can work in the anticausal setting. And empirically, people have found that semi-supervised learning sometimes worked and sometimes it didn't work without maybe really understanding what characterized those two classes of problems. But when we analyzed the results of previous studies, we found that semi-supervised learning very nicely failed in all the cases where the underlying prediction problem was causal, according to our definition, thus confirming this hypothesis. It also turned out that all previous attempts to motivate semi-supervised learning by what people thought were reasonable assumptions can actually be linked to this causal assumption. Now the final example is a very interesting topic, I think. It's about this Kepler satellite or space telescope, which was launched in 2009 to observe a tiny fraction of our Milky Way in search of exoplanets. The spacecraft is named, or the telescope is named after the astronomer Kepler, and it has been staring at the same patch of sky here in this constellation of Cygnus for more than 4 years. And in this patch, it observed the brightness of 150,000 stars, taking a picture like this one down here once every half hour. So this space telescope Kepler tries to detect exoplanets by the so-called transit method. This means that it tries to find planets that pass in front of their host star. This leads to a slight dip in the light curve, as we see it from here. Now you can think about how big this signal should be just by imagining you're sitting somewhere in space and you want to detect our own planet Earth using this method. And just if you think about the size of the Earth, it's about 100 times smaller in diameter than the Sun. We need to square this number. In the end, we find that the signal is the size of the signal is 84 parts per million. It's visible for about half a day. That's the time it takes the Earth to pass in front of the Sun. And it should be visible statistically from about 0.5% of all directions, because you have to be aligned with the plane of our solar system, roughly, to see it. Using this method, by now, thousands of planets have been found, many of them by this Kepler telescope. Some of them are habitable in the sense of we think they allow liquid water, but all of those are around stars cooler and smaller than the Sun. Now, unfortunately, both the spacecraft and the stars vary, and this leads to changes that are sometimes much bigger than the signal. Now, each star is made up of a number of pixels, and from the fact that these pixel light curves are quite different, we can already see that we have a problem. Now, the astronomers have developed a data processing pipeline that tries to remove all these systematic errors, for instance, pointing errors of the spacecraft, and this leads to this thing here called the PDC flux curve. And you can see it's still wiggling around quite a bit. Here we see an exoplanet. This is a pretty big one, so it's clearly visible even though this thing wiggles. Now we've built, and I'm almost done, we've built a causal model that tries to improve upon this. And in the simplest case, this model assumes that the measurement of interest, which is this thing here, the star that we measure, is a sum of an underlying true star, that's the real signal we want to get, and noise sources n over here. We assume that the other stars, modeled or denoted by this x, are affected by the same noise, and at the same time we assume that they're causally independent of the true star that we want to reconstruct, which makes sense because they are light years apart. So in this case, if we additionally assume that all the information about the noise is actually present in the other star's measurement, so everything we need to know about the noise should also affect the other stars, then we can actually prove mathematically that we can reconstruct the noise contamination by regression of y on x. So basically the idea is we predict the star y from the other stars, and since the underlying star is causally independent of the other stars, the only thing we pick up is the noise, which we can then remove. So the light curve that astronomers are currently working with is shown at the bottom here, and ours for this star above, and you can see it's much cleaner. And this is quite exciting for us because, of course, we're hoping to eventually find new exoplanets this way. So let me conclude. I count myself lucky to be standing here receiving this award, and I feel that I don't deserve to be singled out this way. I told you overall story that's made up of many individual pieces and insights, and those were contributed, many of them were contributed by my direct co-workers in Tübingen, shown here, and of course also by our discipline at large. So I'm very happy that some of the people from our discipline are here with us tonight, and I want to name them and thank them both personally and as representatives of our discipline. So I've named them all over here, starting with Michael Black, my co-founder of our institute in Tübingen. I'm very happy that he's here as well. And I also want to thank my PhD supervisor and my friends who came here, especially those whom I met 23 years ago when I came to London as an exchange student and had a great time here. And finally, and especially, I want to thank my lovely family down here. Thank you very much.
We wish we had more time for more information. Thank you so much. Now, we wanted to give a bit of time for questions. There are microphones. So if you want to ask a question, please put your hand up and wait for the microphone to come. And I've got Stefan. Do we want to go to Stefan first? All right, and then we'll come to you, sir. So Stefan's doing the online webcast question.
So this is the question from the web. So machine learning is about optimization. What could be done to take optimization to innovation and creativity from a machine?
So I'm not sure I completely agree with the statement that machine learning is about optimization. Machine learning uses optimization, but of course the central questions like generalization you can talk about without asking the question how you will eventually optimize certain quantities. So but of course, the second part, how do we take this to innovation and creativity? That's something that we don't really understand. So it seems funny that I think there will always be certain things where humans seem to be better than machines, and currently, certainly, creativity is one of them. But if you had passed, I think we were discussing a similar topic before, if you had asked people 50 years ago, they would have said chess playing is something that humans are much better than machines, and machines will never be able to do it. Maybe people would have thought once we can beat a grandmaster in chess, we will have understood intelligence. So maybe it's good that there are always these things where we think we're better.
The gentleman there in the...
So you were saying that these methods work for large dimensional data where you have lots of data, and I was wondering whether this depends on some sort of fairly low dimensional structure that exists in the data, and whether these methods could succeed even if there was no such low dimensional structure in the data.
Yes, I think that's a very good question. So maybe one can give a two-part answer. So if it's only about making a guarantee in the sense of we will do as well in the future as we have done in the past, then we can make statements that are actually independent of this structure. But then we will find that in order to give a good result on the training data, we will need to use a model that has very high capacity. So there's an example that I can sometimes give. If you wanted to learn the mapping from the name in the telephone directory to the telephone number, so that's a very complicated high-dimensional mapping, then you would find that either you have to use a very, very complex model, which would then also have high capacity, in which case we might be able to explain the training data, but we will not be able to generalize to the test data, or we will use a low capacity model with, for instance, a large margin, but then we will find, so in this case we will find that the training performance does not mislead us about the test performance, but the training performance will already be bad. So therefore, in a sense, this guarantee maybe doesn't help us so much, and then your question actually becomes maybe more specifically whether we are able to find function classes which do have low capacity and at the same time they work for the high dimensional problems that we're interested in. And I think this probably will only be possible if the high dimensional problems do have some structure that we can comprehend and model. So yes, I think in this case we do need additional, possibly low-dimensional structure in the data.
There's a gentleman there with glasses on. Stefan, are you going to have another one?
Yeah, I think there's a good one here.
Okay, so we'll come to you next, and then there was someone over here. Yeah. Okay.
Which are we doing? Right.
You've got the mic.
Right, okay. There is a fundamental aspect of the machine world which you touched on, but really is a disadvantage, I would suggest, in the applications. And that is that all the examples you showed, all the equations, must, by definition, be homogeneous through time. If they're not homogeneous through time, it doesn't actually mean anything. I mean, you're dealing with bits and bytes, numbers, equations, and the rest of it. But as soon as you apply it to people, the problem is that people are not homogeneous through time. They are, creativity is a point in question there. People do things which are totally unexpected and cannot be forecast. And this differentiation between homogeneity through time and non-homogeneity through time was pointed out by John Maynard Keynes in respect of economics. Now, he was furious when people started turning his economics into equations for just that reason. And you can see the results now, where economists have beautiful equations. I mean, yards and yards of equations, or perhaps they should be meters. And it doesn't work. It doesn't work, and what they do is to blame people for it. And
That's
what kind of sense is that?
Let's take the answer.
I completely agree that if things change over time, we can be in arbitrarily large problems. And in fact, I think the same kind of problems also affect us as humans. I think your example of the economy shows that. So if something fundamentally changes, then if a bubble bursts, then suddenly everybody who is an expert on the economy is completely wrong, and things go another way. So I think it's a fundamental problem that we can't circumvent, and we can only try to get better at it, but it's difficult.
Stefan?
Do we have time for one or two questions?
One,
Depends.
I think, because
Okay.
we've got a question here, and I'm supposed to finish at 7:30.
Okay, I'll take the first one that came in then in that case. Do you see a relationship between your work on kernels and causality?
Yes, that's a good question, yes. So I actually had some, while I was working on this, I did have some, or while I was preparing this talk, I was specifically thinking about this problem a lot. And I see more relationship now than I saw in the past. So there are certainly already links in the sense that the best existing methods for conditional independence testing are actually based on these kernel mean embeddings. So we use those in causality as well. But I think there might be closer connections in the sense of, I think it's possible to embed causal systems in reproducing kernel Hilbert spaces in a meaningful way, and use these embeddings also for detecting or verifying causal structures. So I think that's a fascinating topic. So I don't have a final answer yet, but I think that's a promising direction.
How applicable these techniques are to semantic networks and natural language processing?
It's also an interesting question. Maybe you could answer this better, but I think, maybe a partial answer could be that some of this potentially could be used to learn certain semantic structures. So certainly if the training data is something that's, for instance, produced by humans who assign certain semantic meanings to different things, then we could try to extract this kind of knowledge from the training data and then come up with systems that have some kind of semantics built in. But maybe I have to pass this question on.
Oh, no, I'm not going to take that here, but it's really interesting because we were talking about all this before the lecture, weren't we? So it is dead on 7:30. I'm supposed to stop now. So they've been fantastic questions, actually, following a fantastic lecture. I have to say that one of the criteria for the award is we asked the nominators to assess whether if this person won the award, they would give a good lecture. Well, And what we don't say is that we could take the award back if the lecture isn't very good. Well, but we talk.
Worry all the time.
Well, we talked about this beforehand. I would like to say what I think you will have seen here an example of an excellent lecture explaining really quite a difficult topic in a way that's publicly understandable. And I thoroughly enjoyed it, and I would have been happy for it to go on for much longer. So I think you have fulfilled the last criteria for the award. And so it's now my pleasure to give you your scroll, your medal, and your cheque. And ladies and gentlemen, would you thank Professor Schölkopf for such a wonderful lecture tonight? Thank you.